Hi everyone. The topic which we are going to discuss is how to design a thread component in SolidWorks. So myself, name MGS, and topic is thread design. So from Shiksha Juniors, I'll move to the next slide. Uh, Content. What we are going to discuss on the entire session is introduction on threads and screw threads, manufacturing of threaded fasteners, plating and coatings, some information regarding threaded fasteners and how to make threads in SolidWorks. So introduction. What is a fastener? So fastener is a device which will join two or more components together. So mechanically, when you come to the fastener, like there are different categories which are there. So temporary fasteners, semi-permanent fasteners, permanent fasteners. So when you come to the permanent fasteners, these are like you have seen on welding, bracing, so which will you will not be able to separate them. You have to in order to separate, you need to destruct the material, the base material. So that is why they are called permanent fasteners. Semi-permanent, where two components are joined together in permanent way, but when you want to remove them, so you destruct the component which is holding them, not the base material. Whereas the temporary fasteners, where you don't make a disturbance to the base material, even the part which is combining them. So that is why temporary fasteners. So our agenda is to discuss on the threaded fasteners. So they come in the category of temporary fasteners. So we'll concentrate on this area to discuss in this session. In the threaded fasteners, I'll explain on the fundamentals or the nomenclature which are involved in the screw fasteners. So these are the different terminologies which we need to know before understanding what is a thread and how to design a thread. So when you have a thread, it's divided into two, like external thread and internal thread. External threads are on the shaft, where and internal threads and the nuts are where the shaft will enter into the system. So I have given an example. So what we see here is this part is a internal thread and the shaft is having a thread is external thread. So in the terminology, again, I'll move to the next one. Screw thread. What is a screw thread? The helical movement which you see in this, that is called screw thread. The thread forms when we see the cross section of a thread, so which will pass through the helical is a threaded form. And types of threads, we have a multi-start screw threads and single thread and double start, triple start. So when you see here, a single threads are where you have a one thread continuously running, but when you have a two starts, like two different starts will be there, like which is you can see in two different colors. So and similar way, it's multi-start where you have a more number of threads which are running around on a single shaft. So then I have a like types of rotations in threads. So if you rotate, that is a RS thread and LS thread. So they goes on the thumb rule of right hand and left hand. So in the right hand, when you see this direction, so when you rotate along the fingers, the component moves in the vertical direction. So that is a RS thumb rule and similar to the LS thumb rule, where we have a different rotation. So the application wise, RH is used widely in every uh, subsystems and every applications. But in where there is a theft and anti-rotation is required, where in that places we use LH rotation, because theft wise people will always be thinking the right direction. So, but if you have a negative direction, they will not be able to steal easily these components. Then we have I'll move to the basic what is internal of a thread now. We have a crest, root, flank, pitch, addendum, dedendum, pitch diameter, major diameter, minor diameter, height of thread, thread angle, helix angle, lead helix. So I'll go through each component, what they mean in a thread terminology, and why do we need is to design all these parameters in terms of a thread fasteners. So crust is So when the helix is there, the top portion of the thread which connecting the flank. Okay, this area is called crest. You could see the marked here, and root is the bottom portion of the thread, which is connecting the, again the flanks, the adjacent flanks. So you see here, this is called a root, and flank is the inclined surface which goes from crest to root is called flank. And you have a pitch. So the distance between two any adjacent crest or root, like the pitch which travels in the helix, is called a pitch. Okay, the between two any adjacent points. And we have addendum, dedendum. So the point where you have a height from pitch circle to the top one is addendum, and from pitch position to the bottom root is called dedendum. And pitch diameter, the diameter which is passing through the pitch circle is called pitch diameter, and major diameter is the diameter at the crest position. So where we have a top portion, so is called major diameter, and the diameter which passes through the root position, that is a minor diameter. And we have a height of thread. So the difference between the major diameter and the minor diameter is the height of thread divided by 2. It will be height of thread. So this is from this area to this area, and we have a thread angle. So this is the angle between the two flanks, like two adjacent flanks, or it's between the threads. Okay, so if you have one thread round and another thread round, so between them there is angle making. It's called thread angle. So helix angle and lead angle. So they come when we open this thread. So these angles are defined. So which we'll explain in the later stage. So I'll move to the manufacturing of the threaded fasteners. So why do we need this is like to understand how these components are going to manufacture. Will facilitate to design these components in a better way. So I have a when we have a threaded fasteners to be manufactured. So very first phase is to have a raw material preparation and make a size shape. So since it's a mass produced component, so they don't be going for machining of these components, because that will take a lot of costing and time position. So this is made using a heading operation, which is basically a forging of a component to size the initial shape of the bolt. So we take a raw material and cut into the based on the volumetric calculation. So what is the length of the part is required, and afterwards it will be shaped to intermediate head sizes using a die, and later final size is carried out using a die. So once the final size is made, so we have to next move to the stage, the threading stage, where two many different methods are there. The mass produced one is a rolling method. The less components are made using a cutting method. So there is a little difference between these two. So in the cutting methodology, you remove the material from the component actually. So basically, whatever you see here, this is all removed material using a cutting tool. But when you have a rolled or formed threads, in this the material is deflected to form that shape. So you are not eliminating the material from the system, but you are deflecting it to the shape of the threads. So this way, this will have a higher strength compared to the material which is removed, because since you have eliminated the material from the system, that will have a little stress concentrations coming in the picture. So due to that, the strength of this system is less compared to the formed threads. So once we make threads, then we'll when you see the farm thread, the material is deflected in different directions, right? So due to that, there are heavy stresses induced in the component. So we have to treat them actually. That is where we go to the heat treatment process, where we treat each threaded fastener, and so during this treatment, we heat the component to the around 700 to 600 degrees Celsius and relieve the heat treatment process, and then attain the required hardness. That is called different classes: class 8.8, class 10.9, class 12.9. So those are achieved in the heat treatment. And once we have a heat treatment with the hardening, so again there are thermal stresses also induced in that. So in order to relieve all these stresses, we carry out stress relieving, where we heat to the lower temperature around 400 to 300 degrees Celsius, and slowly gradually cool the system to achieve the stress relieving. So this way fasteners are manufactured. So once we have a fastener manufactured, it's very important to have a resistance to the corrosion, because these components are exposed to many harsh environment. To avoid corrosion or reduce the corrosion of a components, we have a plating and coating on the system. So there are different methodologies used to coat fasteners. So if we, there are different materials. One is zinc, cadmium, nickel, and chrome. So in the zinc, again, there are different varieties. In the coating process, what they do is they take up zinc as a main element. So they try to give up the zinc. Basically, in corrosion, what we do, we have a base material and we have a material which is getting corroded. So in this case, so what we are trying to keep is the main material constant and adding a preferential material which will give up its electrons to the corrosion environment. So that is zinc, cadmium, or nickel, chromium. These are the preferential elements. So now in the zinc, we have three different coatings which are based on the color, and to avoid get these colors, there are different elements added along with the zinc to attain these colors. We have a blank, we have a white or a blue, and we have a yellow. And yellow is currently as a environment act, it is avoided now due to there is a poisonous item which is present in this. So currently mainly used is now is uh, black and blue. So cadmium is having a yellow, so the zinc yellow is eliminated and added a cadmium yellow, and then the cadmium white. So these are all again the different process. So the zinc is the lowest corrosion resistance and it increases harder. The cadmium one will have a little more, and nickel will have a much more higher. And chrome is the one which is having the highest corrosion resistance activity. So and then even the shininess also increases with respect to chrome plating. So this is where used in many food grade industries and the sophisticated applications, but these are all used in industrial applications, and nickel and all this is used in like electronics equipment. So this is about coating. So we'll move to the main topic on the threaded profiles and forms. So there are many different thread forms which are formed based on the different standards and based on the different applications requirement. We have a metric thread, American National Unified Thread, stub threads, square thread, acme thread, and buttress, knuckle, and Whitworth threads. So all have their own different applications. I will discuss them in the later stages in the details. And we have a metric thread. So currently we'll focus on the metric thread because metric thread is the one which is widely used across the industries. Even in Indian standards, metric is the one which is followed, IS metric or ISO metric, and entire industry like across Europe and US, they use ANSI, ANSI and metric and ANSI inch. So, but majority of them also still prefer metric system. So we'll discuss on the metric thread details and how to make a one component using a metric threads. So this is a metric thread details where we have a different terminology which we discussed in the previous slides. So these values will take up from the standards and then make a component from this. So in this we have a threads which is M20. So there are different sizes of the threads which are there based on the requirement and strength requirement. So we'll do the discussion on M20 thread, which is a regular threads which we use and which with the 2.5 mm pitch and 100 mm length hexagonal bolt we are going to make now. Okay, so this is according to standards. These are the dimensions which we need to maintain and with the values given in the table. Okay, so we have a head and we have a the shank and we have a threaded portions which we need to develop. So in the process, so what we saw in the process, like we initially make a head position. So we'll also try to make a head and then we'll make a shank and then we'll make a thread. So this is the process we are going to follow in the next slides. So these are the dimensions which is required to input to make this component. Okay. So let's open the SolidWorks and start the making the component. So we go to the file and click on the part and click OK. So here part there are many templates which are available. Take any template which is available so that we make a component of this and click OK. So next we'll move to the slide. So in this we have to initially we what we discussed is to make a head. So let's make a head. So how do we make a head? This is a hexagonal size component. So we'll go to the sketch and click on the plane where we want to create a sketch. So let's go to the right plane and press a Control 8, or there is a when you press here there is a normal view which you can press. So to make the screen normal for the sketching. So after that, click. Now we'll move to the component which is a hexagonal size. So click on the polygon which is available in the sketch bar. So when we click on the polygon, we get a menu where we have to you can take up like different sizes of polygons like 5, 4, 3, or 6, 7, 8 like that. So since our requirement is a hexagon, so let us put a 6 value and then enter the sketch. There are different ways like center one or take the face to face and all. So let's take a center point and then draw a sketch and give a dimensions. When you see here, there are two dimensions which you can see. Two dimension hexagon. We have a face to face, that is across the face width or across the edge, like our corners. You see these corner points. So generally across the face is a even number. So integer number. So we follow this to add this value across the face. So the value we see is a 30 in the across the face S value. Okay. So let's concentrate on that. So we go to the smart dimension and take a smart dimension and add across the face 30 dimensions. And so whenever you do any command operations, you need to exit so that always exit is always visible at the corner of a window, or you can go back to the sketch position of the window, like bar where it is there. So once we have drawn hexagonal part, so let's move to the development of the hexagon body. So now in order to develop the hexagon body, we have to move to the extruded boss, which is there in this option. So you click on the extruded boss and we have menu option where we have to input the requirement. So according to the standards, it states the value should be K, which is equivalent to 12.5 nominal. And there are different values you can put, but we'll take a nominal value in this case. Once we have a nominal value, so input this to blind and then make a projection. So now we have a component developed with respect to hexagon. So and click on the exit. Now once we have the head done, so there is a you could see there is a beta or there is an angle or chamfer which is present. So we have to make this chamfer. So again, go back to the sketch and sketch on the component and draw a circle which is tangent to the hexagonal faces. So once we draw that, we click on that component and then move to the features and chamfers. So when you have a cut extrude feature, you have an angle beta, which we need to input here. So if you go to there is a draft angle, which we need to capture and click on the flip side out since we are cutting the outside of it. So if we click inside, then the entire part will go. But flip side out, if you do, then you will get a chamfered curvature along the circle. So this is required. If we do directly using only chamfer features, you will not get this uniformity in the chamfering of the entire bolt. So which is done according to the lathe operations. So we'll click on this and then click OK. So we have a hexagonal ready with the chamfer. And now let's make a shank. So shank is having a dimensions of 20 Okay, so we'll go to the sketch again and sketch, select this face and make a sketch of 20 diameter circle and click OK. And since after we make the sketch, we have to develop the body. So we have a boss extrude feature again, and come back to the boss extrude. And since our length of the bolt is 100 mm, that is L, so we are going to make a 100 mm length boss extrusion. So and click on the OK. Now we have developed the head with the shank, and we need to develop a thread. So for the thread to be developed, need to add a chamfer at the end. This chamfer can be added later stage or can be added before the thread also after the thread. So generally preferred is before the thread. So we go to the chamfer feature in the system, and then enter the values, and I click OK. So here we have taken a 2.5, so equal to the pitch as a chamfer, so that it numbs the initial start of the thread. Next, we'll move to the development of the thread now. So this is where you should be concentrating more on the thread designs in the SolidWorks, how to make it. So thread portion consists of two items. That is what we discussed in the initially, that is screw thread and thread forms. So now we have to develop a screw thread, which is a helical system, and thread form, which is a cross section of the thread. So first we will go for the screw form development. So in the screw form development, we have a helix to be developed. So helix in SolidWorks, it requires a very basic circle or a base circle on above which this helix can develop. So that is where we create a circle on this face, which is equivalent to the diameter of the shaft. And once we clicked on that, so we'll go to like you can do a search here, helix system, like a command, or there is, if you go to a sketch, there is a helix which is there in the curve actually. So you can refer there, or you can easily search all the commands in this area. So helix, when you search, you'll get a helix command. Click on that helix command, and you'll have opened the helix system. So you enter what is the requirement in our system. So the pitch is 2.5, which we know already. And based on the standards, the length of thread, which is B, should be 46 according to this. So the minimum thread, which is required in the M20 for an engagement, is a 46 mm. So which we will maintain here. Now enter the height as a 46 mm, and keep the start of the thread as 0, or you can do different angle also, but that depends on the where you draw the cross section of the bolt. Click on that and click OK. So now we have a helix developed. So now we have a screw form developed, and now let's do the thread forms. So helix is completed. Now we'll move to the thread forms. In the thread form, we have the cross section of the screw which revolves around the helix. So now, according to the metric standards, so the dimensions are given here. So I'll take from this height, and what is the center pitch width which we have, and P/4, that is 0.63, and the angle 60° which is present. Okay, so 60° angle, 30° angle, again P/8 on the top side. Okay, so once we enter all these values, we have a constraint sketch. And so to get the thread forms in the 3D, then we have to go to once we have this development, we have a sweep cut, the option called sweep cut, where we have to sweep this cross section along the hexagonal and remove that excess material which is present. So we'll go to the sketch profile. So there are three different methodology you can do, but since we have a thread forms profile as a sketch, so we'll go to the sketch profile option. We can try other ones, but they will not be giving the thread forms, but it will give a different forms. But we have our own cross section. Let's try the sketch profile. In the sketch profile, we have our sketch, which we click the form, and then the screw form or the screw thread, which is a helix. So which we click on this. After that, we will able to see a preview of the thread developed on this. So if it is coming good, then click OK. So we have the screw thread formed on the component. So this is how we make a bolt design on a SolidWorks.